I spent most of my last Christmas Eve secluded in my study, working with these very nice people here on problems of celestial mechanics. So you, of course, tell me, why in the world did you do that? Well, there was a party going on just next door. I must say that I don't have the answer to that question yet. Thinking about it hard, but... I would like to tell you about exoplanets, these planets that orbit other stars than our sun. We know now that these planets are ubiquitous in the galaxy. They're everywhere, to the point that next time you go outside at night with your children or grandchildren, you can stare at the skies and tell yourself that each of these twinkling dots have at least one planet. So for millennia, humankind has wondered whether there could be other planets out there similar to the Earth. This we don't know exactly yet, but we are getting there, and this is a big change in paradigm, because now the question is not to know whether there are planets, but how to find Earth 2.0, the next Earth that could be maybe habitable, on which life could have emerged, and so on. So this quest is not only the quest for life beyond Earth, but is the quest to our own origin as well, to better understand how life emerged on the Earth. So you probably know of the discovery, earlier destroyer of this TRAPPIST-1 system that was made by our team and Belgian people and mostly European discovery. And this is a remarkable system, because this tiny star that you can see has only the size of Jupiter, and it is orbited by 7 planets of the size of the Earth. So tell me, why this discovery is significant? And the answer is that it's the first system of Earth-sized planets for which we can probe the atmosphere. In the next 5 to 10 years, we'll be able to say in the atmosphere of this planet whether there's water, carbon dioxide, carbon monoxide, or even ozone that is so important for the Earth. So now we have a window into a world, actually, of planets that we could maybe characterize. So we were very fortunate to detect this system because, as seen from the Earth, this planet passed in front of the star, all the 7 of them. So we are really well aligned with the orbital plane of these planets to see them passing in front of the star regularly. And I would like to show you the data that has been taken, the real data from which we prepared our paper. So at the top, you can see a schematic of the star with the planet passing in front of it. And at the bottom, you see the actual data that was taken. So as each planet passes in front of the disk, you can see a dimming of the light curve. That is at the bottom, is brightness of the star. So it's constant where there's no transit. And when a planet passing in front of it, it produces a little dip. So this is how we recognize these planets. Interestingly, these planets are labeled with different letters. So the B planet is the innermost one, and then you go up to H, the 7th one. And this B planet has an orbital period of 1.5 days. On the Earth, a year lasts 365 days. On this TRAPPIST-1 B planet, it's only 1.5 days. So it's a great news for people who like to party, because it means that you celebrate your birthday 4 times a week there. So when we put our data together, this is a picture that was published in our Nature paper. You can see that at that stage we knew 6 of these planets: planet B, C, D, E, F, and G. But there was an orphan transit, one transit that belonged to a planet that was unknown at that time. And since we had only one thing that appeared, we wanted to have more of this data to constrain the properties of this planet and the orbital period, the duration of a year of this planet. So of course, we had to announce these results. It was public knowledge that there was a 7th planet in this very exciting system. So the race to find this 7th planet had begun. So that's where, actually, we got help from our little friends from the age of enlightenment more than 300 years ago. Because these very people built all the framework to understand the motion and the orbital properties of systems that are like the TRAPPIST-1 system. So what we did is simply to use their work, to combine everything together, and then to try to find the needle in the haystack. So we made a lot of predictions. We had different cases that we wanted to test. And at the end, we had a particular time that we knew this planet would pass in front of this star, and then we would be able to recover this planet. We had new observation of this TRAPPIST-1 system that were publicly available right away, so we were not the only one on the starting line, so the race was really, really there. And 2 hours after we got the data, it was in March earlier this year, well, we found the transit exactly where expected. So those guys, 300 years ago, knew exactly actually about the TRAPPIST stuff. They knew exactly actually where this planet would be. So of course, there was a lot of excitement on Twitter because we wanted to keep this result secret as much as possible. We needed to be fast as well. So after 60 hours after the publication of this data, 450 emails between 30 co-authors and some point 15 co-authors editing the manuscript at the same time, we managed to submit our paper. So it was a great fun. Maybe a bit less for our PhD students, but they did very excellent work on this system. So how did it work? So hopefully there's some sound here. You'll see a video showing you the system, and each planet, when it transits the star, produces a note. And as you go from the H planet here, so the 7th planet, we'll move inwards toward the B planet. So it is periodic. All these notes are periodic, of course, because the orbital motion is about to be periodic. And then as you add the planets, the pitch will evolve. So you get actually to higher frequency as you move inwards. So this is really a celestial harmony. It's not as good as Mozart, I agree, but still it shows you that there's something very nice in this system. But the best part has yet to come. So we're getting closer. We'll get to planet C with a 2.4 days period right now. And then the planet B, the inner one, with a higher frequency. So it becomes high-pitched. So now we need some drums, some percussion. I'm sure you agree. So you'll see that there is something very particular happening here. Very regularly, planets align between themselves. And you have the different drums that happen for different pairs of planets, different kind of drums. You can hear it starts to be very nice. And this is due to the fact that this planet cannot move in random motion. They have to obey strict rules for the system to remain stable and non-chaotic. So then you start to have a kind of jazzy melody that is quite nice to listen to. I wouldn't listen for that for 3 hours, of course, but still, it tells you that this system actually holds together because of this periodicity, because of the celestial harmony that is so nice, actually, the system managed to thrive and to survive. So this was a very nice video done by colleagues in Toronto with musicians and astrophysicists. So the interesting part of this system is the following. If you want to find life, there is a paradigm, is to follow the water, because we know that on Earth, water has been essential for life to emerge. And on the solar system, so the bottom part, you can see that the Earth is comfortably fitting in what we call the habitable zone. It is not a good name, but still, that's the current name. It means that this is the zone, the area, where you can have liquid water at the surface of a planet. You're getting too close, it's too hot, then the water just gets vaporized. You get too far away, your water becomes ice. If you see the TRAPPIST-1 system, there's an enlargement here. You can see that 2 to 3 planets are comfortably sitting in this habitable zone. So there's a chance that maybe these planets could have liquid water at their surface, which makes the system even more interesting, of course. So I would like to show you a tour. So it is an artist's view of the tour of these planets. So they're very close to the stars, so they are tidally locked, meaning that they have a permanent day side and permanent night side. So if you're too hot, you go to the night side. If you're too cold, you move to the day side. But for this temperature here, this is planet C, it's still too hot for us. But as we move farther away, you can see that there's water that will start to appear at the terminator here between the day side that is too hot and the night side that is too cold. You've got the temperature just right between the two. And as you move farther away, water takes over. And you've got oceans, maybe big oceans on the day side, and then you've got a lot of ice on the night side. And as you go farther away, you'll see that the ice takes over, even toward the day side, and which makes actually these planets very interesting, because we can do really comparative exoplanetology. We can compare these planets that were born in the same material, let's say, and we can see how they evolved between each other. So we have a really interesting laboratory when we can study the evolution of these Earth-sized planets. So, of course, we want to find more of these planets. So we are building a telescope in Chile under the Speculoos collaboration. And in Mexico, the University of Bern is leading the building of a new telescope that will be remotely controlled. So there's no human being interacting with the telescope, but it will be looking for other planets similar to the TRAPPIST-1 system, because this is only with the numbers that we'll really be able to build our understanding of the emergence of life in the universe. But the experiments I'm really interested and fascinated about, I think this is one of these things that could be done in Switzerland with all the exchanges and collaboration that we have with industries and universities. It's called MERMOS. And the idea is not to observe exoplanets, at least not yet, but to observe the Earth. because we want to have fingerprints of all the surface patterns that we have on Earth, like the oceans, the deserts, the polar caps, the rainforest. And we want to build an ID of the Earth that we can then use to interpret the data that we get in 5 to 10 years on exoplanets that are distant to 35 or 40 light years away from us. We want to say, in 10 years from now, unambiguously, that there could be rainforests there. There could be cyanobacteria in big oceans or things like that. And we are getting there. We know the techniques to do that. We just need to implement that and to size the instrument accordingly. So to finish, to wrap up, I would like to show you this picture. This picture has been taken by the Voyager 1 space probe that is now the farthest probe that has been sent ever by humankind. In 1991, this probe took a picture of the solar system. And you can recognize a few solar system planets here. You can find our sun toward the left side of the image. If you zoom in on this side and you use all possible knobs to play with the brightness, with the contrast, because this is very low signal, lost in the glare of the sun, you can see a pale blue dot, as Carl Sagan named it. This pale blue dot is home. This is our Earth, lost as a pixel, a blue pixel, in this beautiful image. So I really think that this picture transcends politics, economical interests, cultures, or beliefs, because this point suspended in space is universally shared by 7.6 billion of people. So we have to care for this little dot, we have to preserve it, but more than ever, today, we have to make sure that we show compassion and empathy between each other. Thank you.